course throughout the semester. So before I get going, I also like to start with just telling you a little bit about myself. So my full-time job, I work for Miami-Dade County in the Parks Department at the Deering Estate. I'm in charge of all the education and conservation that's done there. Before I worked at Deering, I worked for the National Marine Fisheries as a biologist, as a fisheries biologist. That's truly my background, is more fisheries. I went to graduate school at the University of Rhode Island and got my master's in oceanography. It's specifically in biochemical oceanography, where I did studies on ocean acidification and the impacts on fish populations. So that's kind of how I got into the fisheries field. So I was more on the data analysis side for the National Marine Fisheries, trying to figure out fish populations to set quotas for the commercial fishing industry. So I worked at the Marine, or the National Marine Fisheries Lab over on Virginia Key, right across from University of Miami's Oceanography campus. So I worked there for about 6 or 7 years. And before that, I worked in Alaska for just over a year as what they call a fisheries observer. So I lived out on the commercial fishing vessels, and I would go out in the Bering Sea as they were catching whatever their target species was. I would go out and sample it and send that data back into the National Marine Fisheries that they would use to help analyze fish populations. I was collecting things like fish sizes, sexes, if they were pregnant or not, just to kind of help with determining the health of an overall species population size. So that way we can use that data to analyze it for the commercial fishing industry. So I spent about a year out on the Bering Sea. So if you've ever watched a show like Deadliest Catch, I was out on boats like that. So there's actually one that was on a couple seasons ago. I was actually on that boat like 15 years ago, 16 years ago. But either way, so that's kind of my background is more fisheries. But my master's degree is in biochemical oceanography. So because of that, that's how I got into teaching this course. So if you have any questions about like my background or any things I've ever done out on the ocean, feel free to ask. Oceanography is something that a lot of people take this class because I know that you have to take a science class, okay? And you're using this as a general education requirement. I try and teach this class that way, knowing that probably one or two of you might be interested in going into the sciences, in marine biology, environmental science, whatever it is. But the majority of you, you're probably in business or nursing or whatever it is, and you're just taking this class because you need that science requirement. And I get that. I was the same way when I was an undergrad, taking history classes because I had to, okay? It wasn't things that I was necessarily interested in. So I try and make this class as easy as possible and as interesting as possible for you, okay? So that way you learn something about the ocean. So I want to make sure that this class really is as easy as possible for you and not super stressful. So as long as you're keeping up on the assignments and making sure you complete things on time, you're going to be fine in this class, okay? It's when you fall behind in completing assignments that things get a little dicey. But as long as you're coming to class, taking notes, and then completing the homeworks and the quizzes, you're going to be totally fine in this course and you've got nothing to worry about. And like I said, I try and teach this in a way that is as basic as possible, okay? Because there's going to be some subjects that come up that can get very complicated, but I try and do it in a way that is going to make it as easy to understand as possible, all right? I'm sure most of you went on ratemyprofessor.com, you saw my reviews, and that's why you're taking this class, figuring that mine was going to be the easiest option. I try and do it that way, okay? That's kind of the goal in this course. So let's get going though, okay? So we're going to start off with chapter 1. Tonight, this is really just an intro. This is kind of an overview of kind of what to expect this semester, kind of what oceanography is, some of the things that we study in oceanography, and it's really just an overview of what to expect throughout this semester. So, what is oceanography? So most people, when they take this class, they think it's going to be marine biology. Marine biology has to do with the study of life within the ocean. Oceanography is kind of the overarching study of the ocean. It has to do with every single element of the marine environment. So in its truest definition, it's just the study of the marine environment. So something like marine biology, that's part of oceanography. This class is going to be a little bit of everything that has to do with the ocean. And there's going to be certain things that we talk about that you wouldn't think has to do with the ocean, but it does have to do with the ocean. Things like earthquakes, okay, or volcanic eruptions. That's actually part of oceanography. So that's why, like, I want to make clear that this is not going to be just talking about plants and animals within the ocean. That's going to be part of it. We are going to do that stuff at the end of the semester, but we are going to touch on every single little element of the ocean to kind of give you an overview of all the different elements of oceanography. So like I said, it's not just marine biology, okay? It's every single aspect of the ocean. That's what this class is going to be about. So why do we study the ocean? Why do we even care? There's a lot of different reasons. For me, it was always the fishing industry. I grew up fishing. That's kind of where I got my interest in the fishing industry, and went into school knowing that that's what I wanted to do. So some people study it for the fishing industry. It's a big economic resource for us. Some people study it for global warming, okay? If you don't believe in global warming being influenced by the human population, I'll prove you wrong in this class and show you exactly how it is being influenced by the human population. That's one of the topics that we'll go over this semester. El Nino and La Nina patterns, those are weather patterns that we'll go over this semester. It's really important here in South Florida because that also impacts our hurricane seasons. So we'll talk about hurricanes and El Nino versus La Nina and what that means. Some people study it for coastal pollution reasons. People like going to the beach. They don't want to see trash everywhere. There's certain things in the ocean that you cannot see that is a pollutant, things like mercury, different types of nutrients. Too much nutrients in the ocean is not a good thing. So we'll talk all about that type of stuff as well. Beaches, things like sea level rise, what the impacts are to the beaches due to sea level rise, especially here in South Florida. We'll talk about what those potential impacts are of sea level rise. Some people study the ocean just because they're curious about it. Somebody kind of, who's a good example? James Cameron, the director. So James Cameron is the director. He did like Avatar. A lot of the stuff that you see in Avatar, he's actually drawn inspiration from the ocean, okay? He's seen things in the deep parts of the ocean. He uses that inspiration to create different characters and different things within like the Avatar realm, okay? The Avatar world, those movies. So those are just some examples of why we study the ocean. There's more. It's just different examples. This picture here is actually from one of the vessels that I was on. They were fishing for pollock out in the Bering Sea. Pollock is a really disgusting fish, but it's used. If you ever go to McDonald's and get a fish fillet, they say it's cod. If they say it's Pacific cod, it's not. It's mostly pollock. It's like 90% pollock and then 10% cod. Because there's cod in it, they're allowed to say it. It's not false advertising, but it's primarily pollock. Pollock sells for about 6 cents a pound. It's a really, really cheap, disgusting fish. So if you like the fish fillets from McDonald's or Wendy's or any of those places, that's really what you're eating, okay, is pollock. It's not cod. So it's just as a FYI. All right, so there's 4 main fields to oceanography. It's what we call geological, chemical, physical, biological. Those are the 4 main ones. Those are what we're going to talk about throughout the semester. Each class is basically going to cover one of those subjects. It's either going to be geological, chemical, physical, or biological. So what does that mean? Physical, it's basically movement. How does the water move within the ocean? Through currents, through waves, through the winds, okay? Anything that's moving, that's physical oceanography. Whereas chemical, that has to do with the makeup of the water. What's in the actual water itself? What is the chemical composition? What are the marine pollutants within the water? Okay, so the makeup of the water, that's chemical. We will do chemical oceanography in this class. Chapter 5, we'll specifically talk about ocean acidification, which if you've never heard of that before, we'll get into it, okay? This picture here is what we call a hydrothermal event. This is in the deeper parts of the ocean. You can see that it's shooting out black smoke. That water right there is somewhere around 450, 460 degrees Fahrenheit. If you go about 10 feet to the left or 10 feet to the right, that water is about 36 degrees Fahrenheit. It's a very concentrated area where that water is superheated because of stuff that's coming up from inside planet Earth. There's a whole bunch of white stuff that you can see on this hydrothermal vent. Those are all living organisms, okay, that live in these extreme environments. They're what we call extremophiles. There's a lot of different life there. But like I said, that water is 450, 460 degrees Fahrenheit. Very, very extreme environment. And they only live on that hydrothermal vent. If they were going 10 feet to the left or 10 feet to the right, that temperature change going from 450, 460 degrees Fahrenheit down to 36 degrees Fahrenheit, they can't survive that. So they're only adapted to live right at these hydrothermal vents. We'll talk about hydrothermal vents in this class later in the semester because there's a lot of really unique chemical properties within those hydrothermal vents. All right, next, biological oceanography. This is more of your marine bio. This is the study of life, plants and organisms, how they live in the ocean, what are their adaptations, what's their life cycle, just overall life within the ocean, okay? That's biological oceanography. So these are some of the deep water fish. This is called a viper fish. And the shrimp here is utilizing bioluminescence. We'll talk about what that is later in the semester, what that means. And then finally, there's geological oceanography. Geological is basically the study of rocks, okay? The structures, the rocks within the ocean, how things are made, how land formations are made. That's actually geological oceanography, okay? So we'll go over earthquakes, volcanic eruptions, land formations, okay? Something like Pangea and how it broke apart due to plate tectonics. That's all geological oceanography. That's actually going to be next week that we talk about that stuff. But that's a subset of oceanography. So with those four categories, the biological, the physical, the chemical, the geological, those four together, that's what makes up this course, okay? That's oceanography as a whole. Now with oceanography, a lot of times you're not just studying physical, you're not just studying geological or chemical or biological. A lot of times you're studying multiple fields. So it's called biophysical, geophysical, geochemical, biochemical. It can be multiple fields at the same time. But as a whole, the core four are biological, physical, chemical, geological. Okay, so the ocean, it's the most prominent features on planet Earth, okay? The oceans cover up about 71% of Earth's surface. That's why we're called the blue planet, okay? Because we're primarily water. So it's important to understand that because that's what the bulk of planet Earth is. We are mostly water. 71% roughly is ocean water. We think that life, because the oceans are such a dominant feature here on planet Earth, we think that the origin and development of life on planet Earth is somehow connected to the ocean. It either started in the ocean and came up on land, or life started close to the ocean and moved its way into the ocean. Because of the long history and the sheer size of the oceans, it would just make sense that the oceans have some sort of connection to the development of life here on planet Earth. Now, Earth really is just one giant ocean, okay? All the oceans are connected, but we divide them into different oceans, okay? But really, when you look at it, all the oceans are connected. But like I said, they're divided into four, some people will argue 5 oceans, okay? There's the Pacific Ocean, the Atlantic Ocean, the Indian Ocean, and the Arctic Ocean. Those 4, everybody agrees, those are oceans. The Southern or Antarctic Ocean, people will argue that's not an ocean, okay? I was taught it was, but some people will argue it is not. The reason some people will not consider the Southern or the Antarctic an ocean is because it's ice, okay? It's a big block of ice. Ice is just frozen water. So you can go either way with it, okay? If you say there's 4, you're not wrong. If you say there's 5 oceans, you're not wrong either. If you say there's 1 ocean, you're technically not wrong either because they're all connected. But as for this course, we're going to say that there's 4 principal oceans and 1 other one, okay? The Pacific, the Atlantic, the Indian, and the Arctic are the 4 principal oceans. And then there's one that you can argue, the Southern or the Antarctic Ocean, because it's ice. So this map here shows planet Earth if it was flat, what Earth would look like, and it's actually showing what Earth would look like if you extracted all the water out of it. So there's a lot of features that you can see on the ocean floor here that we're going to talk about next class, okay? Something like the mid-ocean ridge, the Pacific Ring of Fire. These are all things we'll talk about next class. Okay, to compare the oceans to the land, you can see that basically the square mileage. The point I'm trying to make with this table, really what I want you to see is the oceans just are significantly, there's more square footage, square miles of ocean. There is more depth to certain oceans, okay? So the Pacific Ocean as a whole is the biggest ocean, okay? It's almost double the size of the Atlantic. The Pacific Ocean is also on average the deepest of the oceans, okay? Because the Pacific has a very specific feature in it that makes it the deepest, which we're going to talk about here in a second. But that's really the main point I want to make on this table. The Pacific is the largest, and it's also the deepest, okay? You don't need to know specific numbers. You don't need to know that the Atlantic is the next biggest, then the Indian, then the Southern, then the Arctic, okay? I don't care about that. What I want you to know, Pacific Ocean is the largest, and it's also on average the deepest. Comparing oceans to land, okay, you can see that the oceans in this graph here, this pie chart, the oceans make up most of Earth's surface. This pie chart here shows that the Pacific makes up most of the oceans, okay? Now, when you compare, this is going to sound kind of funny. When you compare the ocean's depth to land's height, the oceans on average are deeper than land is tall, okay? So the oceans are deeper on average than land is tall on planet Earth. Does that make sense? Does everybody understand what I'm saying there? That the oceans on average are deeper than land on planet Earth is tall, the height of land on planet Earth.
Yes.
Okay, so we're going to start with the Pacific Ocean. So the Pacific Ocean, like I said, that's the biggest out of the 4 principal oceans. Counts for more than half of Earth's ocean space. It's also the deepest. It's also got one of the coolest geographic features. This line of orange that surrounds the Pacific Ocean is what we call the Pacific Ring of Fire. It's basically a chain of active volcanoes, okay? And we're going to get into this next class, but it has to do with what we call plate tectonics and how the plates are moving underneath us. But the Pacific Ocean is surrounded by a chain of active volcanoes. So you can see just how many active volcanoes there are on planet Earth. They all surround the Pacific Ocean. But the Pacific Ocean also has the deepest point on planet Earth. So the Mariana Trench is the deepest point on planet Earth. It's about 36,000 feet down into the ocean. Mount Everest, which is the highest point on planet Earth, is 29,000 feet tall. You can take Mount Everest, stick it inside the Mariana Trench, and still have about 7,000 feet left over. That's how deep the Mariana Trench is. In the Mariana Trench, we've been to the bottom, okay? We've been down to the deepest point in the Mariana Trench. James Cameron, I'm going to go back to him. He's actually been to the bottom of the Mariana Trench, in a one-man submarine that he funded probably 10, 15 years ago. But that's the Mariana Trench, okay? The deepest point on planet Earth is found within the Pacific Ocean. It's also what skews the average a little bit of the Pacific Ocean being the deepest. It's because it's got the Mariana Trench inside of it. So this just shows you taking Mount Everest, stick it inside the Mariana Trench, And this is just showing you how much space would be left over. All right. So here's China. Go out to the Mariana Islands, okay, directly east of China. That's where the Mariana Trench is, okay? It's out off there, off the Mariana Islands. Okay, then the Atlantic, the Indian, again, this is stuff I don't care if you know, okay? It's just stats about the different oceans. I'm really more concerned, the Pacific is the biggest and the deepest. Okay, we also have these things called seas on planet Earth. Seas are very similar to oceans. Oceans are big bodies of salt water, okay? Now, that's what makes an ocean an ocean. It's got to be massive in size, it's got to be deep, and it's got to be made out of salt water. Seas are a little bit different. Seas also made with salt water, but they're a lot smaller and they're a lot shallower than an ocean, okay? So that's going to be the big designation between a sea versus an ocean. They're both salt water, it's just seas are a lot smaller, a lot shallower. Seas also pretty much completely enclosed by lands, and they have some sort of direct connection to the ocean. They've got one outlet into the ocean. So there's 7 seas. Again, I don't care if you know the names of the 7 seas, but I want you to know, excuse me, what the difference is between a sea and an ocean. Seas are just smaller, shallower versions of an ocean. Still salt water, but they're a lot smaller. So like the Mediterranean is a good example, which you can see in between Europe and Africa. You can see it's a lot smaller than the Atlantic, pretty much completely enclosed by land, but it does have one outlet into the Atlantic Ocean. So that's what's going to make it a sea versus an ocean. All right, we already went over this. This is just saying that oceans on average are deeper than land is tall. Okay, so the oceans, from an early archaeological perspective, we know that the oceans were used very early on in primitive societies as a highway, okay? That societies were using the ocean to travel, to go trade, to go look for food sources, to explore, to find new lands. So it was essentially the earliest version of a highway, okay? Very early on, societies were using these really primitive style canoes, specifically in the Pacific Islands. That's where we have some of the earliest civilizations was on the Pacific Islands. This is the type of stuff that they were traveling in. And you can only imagine they go out into the Pacific Ocean, all of a sudden they're taking on 20-foot waves. That thing's not going to last. But they were using the oceans to get from island to island. So what ended up happening throughout history was whoever could basically have the biggest, baddest navy, whoever utilized the oceans the best, was the most powerful society at that time, okay? Whoever could control the oceans controlled the world back then. That's really what it came down to, was how good were you at utilizing the oceans? Since it was the way that we got from society or culture to culture, was utilizing those oceans, okay? So, all right, there's a question in this chat that says, would you say that seas are part of oceans or are they categorized as 2 separate things? So that's a good question. Seas are not all seas are part of oceans, but seas are separate, okay? They're a separate category. It kind of comes down to, like I said earlier with the oceans, all the oceans are connected. So there really is only one massive ocean on planet Earth. The seas are typically connected to the ocean. So seas are part of the ocean, but they're a category on its own because they have different features to them than what we have categorized the 4 principal oceans as. Does that make sense, Nicole, what I just said?
Yes, it does.
Okay, perfect. Okay, so I already mentioned this, but the Pacific Islands, we know we have archaeological records of those societies going from island to island to trade, to conquer, to explore. They were using those very early primitive style canoes to get from one island to the next, okay? As people evolved,
as technology evolved, societies evolved with it, their technology improved, they were able to figure out things with the ocean to become the more dominant societies. So like the Phoenicians were next. They were the first ones to be able to figure out how to use the stars to pinpoint locations, okay? So that's how they were able to develop navigation arts. So because of that, they could get from point A to point B more reliably because they knew where they were going. So they started to kind of take over. The Phoenicians were the next really big dominant society because they knew how to navigate the oceans. So they would go all over Europe and Africa. Really, it says to trade goods. It really wasn't to trade goods. It was really to go and conquer, okay? To take over other areas and take over other lands, take over other societies. But because they knew how to utilize the stars and they developed better sailing mechanisms, okay, sailing vessels, they could really utilize the oceans to their advantage. So they primarily stayed in the Mediterranean Sea, but they would shoot out into the Atlantic. But their navigation skills really put them on top of the world at the time because they knew how to utilize the ocean to their advantage. Then, once society continued to evolve, people got smarter, technology improved, okay? In the late 1400s, Spain really started to come into its own and really start to dominate kind of the world. And the reason they did that was because they would hire really skilled navigators to go out and explore, find new areas to trade with or areas to conquer, and really start to figure out how to utilize the oceans to the best that they could. So they hired somebody like Christopher Columbus, to go out and find new trade routes to Asia because Asia had certain resources that Spain wanted to be able to utilize to trade, to make money, and really start to take over the world. One of the big misconceptions is Columbus landed in the United States. Columbus never landed in the United States, okay? He landed in North America. He just didn't land in the United States. There was also already people here in the United States when Columbus was around, so it's just one of those things. I don't know why we celebrate Columbus Day, but either way. Columbus, hired by Spain to go out, explore, find new trade routes. But really, it was in the late 1400s, okay, after Columbus, that Ferdinand Magellan, another Spanish sailor, was hired to circumnavigate the globe by sailing. What that means was that he took out a vessel, he took out a couple sailboats, he left Spain, and he went around the entire world just utilizing the oceans. All the oceans are connected, so he was able to leave from Spain, go all the way through the Atlantic, pass through, get to the Pacific Ocean, and then return. Magellan actually didn't complete his journey in the early 1500s. He landed in the Pacific Islands and was actually killed. The islanders killed him and about 70% of his crew. So it was actually his one of the other people on the vessel that completed the journey. They were able to get out of the Pacific Islands and complete the voyage. But Magellan actually never completed the circumnavigation. His vessels did, though. He just wasn't a part of it. So you can see his journey is in the blue, okay? The red is Columbus. The blue is Magellan. So at the tip of South America, there's a pass there that goes from the Atlantic to the Pacific. That's called the Strait of Magellan because he's the first person on record to do this, okay? To go all the way across the Atlantic, down into the Pacific Ocean, across the Pacific, through the Indian Ocean, back into the Atlantic, and back up to Spain. And again, he was killed out in the Pacific Islands. But this voyage took about 3 years, okay? That's how long it took for them to leave and return to Spain. So after Spain was doing all this, England started to come into its own as well and started to really take over and really start to build up their navy. But what England did was they hired somebody by the name of Captain James Cook. James Cook is the one name you need to know in this class. James Cook was essentially the first oceanographer. James Cook was hired by England to go out and do voyages to really study the ocean and try and understand how it works, to do some mapping, to do measurements of depth, to do measurements of how currents work, to do measurements of tides, and really systematically study the ocean. So he was the first person to really do this, okay? So he's what we call the founder, the godfather, the father of oceanography, is James Cook. He did multiple voyages, scientific voyages, over about a 40-year span, where he just went up and down throughout all the oceans, systematically taking measurements to look at how things work in the ocean. And then he would take that information back to England, so England could then analyze it, figure out what's going on, and then how to use that to their advantage for their Navy. We don't do that today, okay? That's not how we do things in oceanography. James Cook, it took a long time for him to do that type of work. Today, we've got modern day technology. We've got sonar equipment, which is using sound signals. We've got robotics. We've got computers. We've got satellites. When I was in graduate school, my school was in Rhode Island. Our research vessel could be in the Mediterranean Sea, and I would be controlling the robotic that you see here at the bottom of the Mediterranean Sea from Rhode Island, okay? So we've got new things that make it a lot easier to study the ocean. But even with those new technologies that we have to study the ocean, we still actually know less about the ocean than we do space, okay? We know actually very little about the ocean because it is such a large area and it's very, very difficult to study. As you move into the deeper parts of the ocean, there's a lot of pressure down there. So the equipment's got to be really good. It's really, really difficult to study the ocean. But with modern day technology, and as we continue to improve our technology, it's getting easier, but we still don't know a lot about the oceans. But when we explore the ocean, we still utilize the scientific method. If you remember this from your high school science classes. So we still, in a way, still utilize the scientific method, okay? If it's the standard in which we determine if something is happening in nature because of X, Y, and Z or not. So if you remember from your high school science classes, when you start the scientific method, you observe something in nature, okay? And then you make a hypothesis. This is happening because of blah, 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 blah. And then you test it. And you keep testing it. You keep testing your hypothesis. And you test it, and you test it, and you test it, and you test it. If you get something that disproves your hypothesis, you start over, and you create a new hypothesis. But if you get the same result every single time that proves your hypothesis, you can eventually develop what we call a theory. And in the science world, we always operate in theories. Theories are different than in absolute truths. Theories, we are 99% certain that this is happening because of X, Y, and Z. We're not 100% certain. Scientists don't like to work in absolute truths. The reason for that is, as technology improves, we can always disprove a theory. It's not an absolute truth. So we could think one thing, and this is the widely accepted theory on why this is happening, but as society advances, technology advances, we might be able to disprove that. So that's why we always work in theories and not in absolute truths. So one of the theories that we have in oceanography has to do with the actual formation of planet Earth, okay? Without the formation of planet Earth, obviously we wouldn't be here, but through the formation of planet Earth, we eventually get the oceans, okay? So the theory that most scientists accept for the formation of planet Earth is what we call the nebular hypothesis. So everybody's heard of the Big Bang Theory. The Big Bang Theory has to do with the formation of our universe, okay, the Milky Way. The nebular hypothesis is part of that, but the nebular hypothesis specifically has to do with the formation of planet Earth and our moon, okay? And again, this is a theory. We are not absolutely certain that this is how it happens, but it's what is most widely accepted in the scientific community on how planet Earth was formed. So what the nebular hypothesis states is that there was a big nebula out in outer space. A nebula is just a cloud of gases and space dust and just material that was floating around in outer space after the Big Bang happens. All this stuff was just floating there. And through a gravitational attraction, the material started to come together. And the material, because they were attracted to one another, okay, they started to pile up on one another. And what they started to form is what we call protoplanets. Protoplanets are just a collection of the nebula, that space dust and space material. There's a gravitational attraction, everything gets pulled together. And they start to form essentially these big blobs of material. And what was happening is you get this giant formation. And it was all pretty much the same stuff, okay? All made up of the same material, that nebula, that space dust and space material. But there's all this other junk floating around in outer space. And it's just bombarding one another. It's all hitting each other because it's outer space, okay? And there's just meteors just hitting one another. And eventually, a meteor struck planet, or what was planet Earth, the proto-Earth, and a big chunk of it broke off. A meteor struck proto-Earth, big chunk of it broke off, and that eventually led to the formation of our moon. That's part of the theory. Again, we're not 100% sure, but that's what's widely accepted on how the moon was formed. As this proto-Earth was being formed, meteor struck it, big chunk of the proto-Earth broke off, floated out, developed into our moon. But as this proto-Earth was forming, it was pretty much all the same material. But as it's getting hit with other meteors, it starts absorbing some of that material that it's getting hit with. And now you start to have different types of material forming. And there's chemical attractions, and there's sharing of protons and electrons, and all this stuff is going on. So you start to form things. Now you're starting to develop what we call density stratification. You're starting to get materials with what we call a high density, and you're starting something like iron and nickel, and you're starting to get stuff with a low density, okay? Stuff that's typically made out of, well, some stuff is carbon, there's oxygen in there as well, but there's a lot of low density stuff. So what density is, you can think of density as weight in a way. It's not the same thing as weight, but you can think of it that way. What density is, it's measuring how much stuff is inside of you. We're all made out of atoms, okay? We've got molecules inside of us. So it's how many of those are inside of us. That's our density. The more molecules, the higher your density is going to be, okay? The less molecules, the less dense you're going to be. So the stuff that was high density, lots of molecules crammed into a tight space, they're going to weigh more, okay? The less dense stuff, less molecules in the same amount of space, they're going to weigh less. The higher your density, you're going to want to go further down. The lower your density, you're going to want to get pushed towards the surface. So what you're starting to see is what we call density stratification. High density material going to the bottom layer, low density material going to the surface layer or the top layer. And you start to form different layers to planet Earth. And we can define these layers a couple different ways, either by their chemical composition, what they are made up of, or the physical properties, what they look like, okay? And these are the different layers of planet Earth. The surface layer, all the way down to the bottom layer. And as you make your way down, you go from low density to high density material. So if we define the layers of planet Earth by its chemical composition, there's 3 layers to planet Earth. There's the crust, the mantle, and the core. The crust is the part we walk on. The mantle is below that, so the material is a little bit more dense. The core is the bottom layer. That's the most dense material. The crust, the mantle, the core. Those are the 3 layers if you define it by its chemical composition. If you define it by what they look like, there's 5 layers. There's the lithosphere, asthenosphere, mesosphere, outer core, inner core. You only need to be concerned about the top two, the lithosphere and the asthenosphere. So the lithosphere, that's the part we walk on, okay? It looks like a cool, rigid shell. The best way to think of it, when you are defining Earth's layers by its physical properties, what it looks like, think of planet Earth as an M&M. The hard candy shell on the outer portion of an M&M, that's the lithosphere. If you crack open an M&M, you're getting into the chocolate, okay? That's the asthenosphere. The lithosphere is the hard part. The asthenosphere, it's kind of liquidy, okay? It's kind of plasticky. So lithosphere, less dense though. The lithosphere is the top layer. So it's going to have less dense, low density material because it's the top layer. It's the part we walk on. Whereas the asthenosphere, it's below the lithosphere. So the material is a little bit more dense, but it's got some give to it. It's kind of like, you can think of it as like a plastic bottle, the way it feels. It's plasticky. It's got some movement to it, allows movement to it. This is going to be important for next week's class when we go over plate tectonics, because a lot of the plate tectonic stuff, it all is related to the asthenosphere, being able to allow some movement. But the asthenosphere, plasticky, it's pretty hot, okay? But it's got more density to it than the lithosphere, okay? Lithosphere, top layer. That's the part we walk on. It's hard, it's rigid, okay? It's the part that we walk on planet Earth. Asthenosphere, below the lithosphere. It's kind of plasticky, but it's got more dense material. Okay, crust. We're going to go back to the chemical composition layers. Again, if you looked at the chemical composition of the different layers of planet Earth, what they're made up of, okay, the crust is the top layer. It's the least dense layer of planet Earth when you're looking at the chemical composition. There's different types of crust. If you guys go and stand on Miami Beach, you're standing on what we call continental crust. The second you put your feet in the water, you are now standing on oceanic crust. If there's ocean above it, that's oceanic crust. You guys walk down into the ocean, okay? You don't walk up into the ocean. The reason you walk down into the ocean, that crust is a little bit more dense, okay? The more dense you are, the further down you're going to be. So that's why oceanic crust material is a little bit different. So it's a little bit more dense than continental crust. So when this density stratification was happening with planet Earth and these different layers were being formed, there was gases trapped inside. Gases are low density, okay? So they want to escape. They want to get up into the surface. So what you started to have happen is what we call isostatic adjustment or outgassing. Gases, water vapor, carbon dioxide, hydrogen, other types of gases like nitrogen, they were all trapped inside those different layers. Those gases wanted to escape because of the density stratification. They're the least dense. Planet Earth and started to form our atmosphere, a very primitive atmosphere at that time. And then eventually, as the atmosphere was starting to form, started to get water vapor, there was developing clouds, things like that, starts to rain, rains a lot, okay, and over 4 billion years of this going on, you eventually start the formation of the oceans, okay? Kind of looks like this. Again, this is over billions and billions of years. This just didn't happen. It took a very long time for this to happen. And we think Earth, or we don't think, we know Earth is about 4.6 billion years old, okay? We know that through carbon dating. It's just a scientific method that you can tell how old something is. So Earth is about 4.6 billion years old, okay? And we think the oceans are anywhere from 3 to 4 billion parts of the oceans. So not all the oceans, parts of them. All right, that's it for chapter 1. Does anybody have any questions about chapter 1? All right, perfect. So before I let you go, Let me stop sharing this one. Okay, 2 things before next class. Let me get back into this one. Okay, 2 things that you need to do before next class. These are both due by midnight next week. Okay, Tuesday night, next week, midnight. You have 2 assignments. The first one, under modules, chapter 1 quiz. Okay, on all material we just went over. Again, when you're ready to take the quiz, you go in there and you open it. Mine's going to look a little messed up right now because I've already opened it, but either way, it'll be there for you to open. Okay, it's 15 questions timed at 30 minutes. Do a week from tonight at midnight. Your other assignment that is due is under discussions. Okay, if you go into discussions, you will see a section here that says meet your classmates. This is your homework assignment for chapter 1. When you click on meet your classmates, there's a section here that says basically tell me a little bit about yourself. What you're going to do is click reply, and you're just going to tell me a little bit about yourself. My name is whatever. I am interested in whatever. What you want to do after I graduate, I want to, whatever. Okay, just tell me a little bit about yourself. When you're done with that, you just click post reply. You're done. That's your chapter 1 homework assignment, okay? Found within discussions. It's called meet your classmates. That's the chapter 1 homework assignment, okay? That's it for tonight. Does anybody have any questions? If you don't have any questions, you're free to go. If you do got questions or you do have questions, I'll stick around and answer anything that comes up.
No question. Thanks so much. Have a wonderful day.
Thank you. You too.
Bye.
Thank you, Professor. Bye.
Thank you, Professor.